Chapter 4. Three major classes of chemical reactions. So far, we discussed the precipitation reactions. In the following, we're going to talk about the acid-base reactions. An acid is a substance that produces hydrogen ions, or we call protons, when dissolved in water. A base is a substance that produces hydroxide ions when dissolved in water. An acid-base reaction is also called neutralization reaction, where the hydrogen ion, hydroxide ion combine to form a water molecule. Hydrogen atom consists of a positive charged proton and a negative charged electron. A hydrogen ion is a hydrogen atom without this electron. In other words, it is just the proton. Now, we already know water has one oxygen, two hydrogen, and the oxygen is partially negative charge. Proton or hydrogen are partially positive charge because the bonds are polar. Okay? Now, if you have a hydrogen ion, the positive hydrogen ion interact with negative charged oxygen. The interaction is so strong, it forms a covalent bond. So here you have oxygen with three hydrogen, with three oxygen-hydrogen bonds, and the whole molecule has a positive charge. And this is called hydronium ion. Okay, so in hydronium ion, the three hydrogens are actually identical. There is no difference among all these hydrogens. Now, this hydronium ion has a positive charge, and this positive charge is stabilized by the partially negative charged oxygen atoms of the surrounding water molecules. And so we can say this hydronium ion is solvated by the water molecules. Here is a list of strong and weak acids, and I hope you still remember from chapter 2. The strong acids include binary acids of halogen atoms, excluding fluorine. So hydrofluoric acid is a weak acid, but hydrochloric, bromic, iodic acids are all strong acids. And oxo acids, nitric acid, sulfuric acid, perchloric acid. If you remember the rule, the number of oxygen minus number of hydrogen is equal or greater than 2. So in this case, it's 3 minus 1 equals 2. And in this case, it's 4 minus 1 equals 3. And these are strong acids. On the other hand, phosphoric acid, 4 minus 3 equals 1, so less than 2. And that's weak acid. Also remember, all organic acids are generally weak acids. So acetic acid is a weak acid. Here's a list of strong and weak bases. Strong bases include group 1 hydroxides. These include lithium hydroxide, sodium hydroxide, potassium, rubidium, cesium hydroxides. And also heavy group 2 hydroxides. These include calcium hydroxide, strontium, barium hydroxides. Weak bases including the compounds containing nitrogen. An example is ammonia. Early in this chapter, we learned that some ionic compounds dissolve in water and conduct electricity, and these compounds are called electrolytes. Soluble ionic compounds, such as sodium chloride, completely dissociate into ions, and therefore they are strong electrolytes. Strong acid, strong bases also dissociate completely into ions, and therefore they are strong electrolytes. For example, sodium hydroxide completely dissociate into sodium ion and hydroxide ion, and therefore Sodium hydroxide is a strong electrolyte. Weak acids and weak bases, on the other hand, only dissociate very little into ions in aqueous solution, and therefore they are weak electrolytes. Acetic acid, for example, in water, it only dissociates into a small degree into ions. So the percent of dissociation is probably less than 5%. So with a small amount of ions in solution, the conductivity is low, and therefore this is a weak electrolyte. Sample problem 4.12. How many hydrogen ions are in 25.3 ml of 1.4 molarity nitric acid? So first, nitric acid is a strong acid. For a strong acid, it will dissociate into ions completely. So what is given in this question is the volume and the molarity for nitric acid. And we want to calculate the number of hydrogen ion. Okay? And therefore, we first calculate the moles of nitric acid. First, you need to convert volume to milliliter to liter, because molarity is defined as moles per liter, and therefore milliliter becomes liter, and then using molarity as a conversion factor to find moles of nitric acid. From moles of nitric acid, we can find moles of hydrogen ion using this stoichiometry, and then moles becomes numbers using Avogadro's number. So here is what we do. We start with volume of milliliter, change to liter. So 1 liter, 1000 milliliter, that gives you volume in liter. And then you times this molarity, which is moles per liter. So cancel volume, give you moles of nitric acid. Okay, so next, using stoichiometry, we find the moles of hydrogen ion. So the moles of nitric acid, this is the ratio, okay, of nitric acid and hydrogen ion. Stoichiometry is 1-to-1 ratio, and that gives you moles of hydrogen ion. And then times Avogadro's number, give you numbers of hydrogen ion. Sample problem 4.13. Write balanced molecular, total ionic, and net ionic equations for the following acid-base reactions and identify the spectator ions. A. Hydrochloric acid and potassium hydroxide. B. Strontium hydroxide, perchloric acid. And C. Barium hydroxide, sulfuric acid. Now first, you may notice that all these acids, hydrochloric acid, perchloric acid, sulfuric acid, are strong acids. So strong acid will ionize or in water dissociate completely into ions. Okay, so that makes a difference. Later you will see if a weak acid, okay, then when you write an ionic reaction, you cannot write hydrogen ion and anion. Instead, you need to write the formula for weak acid. So, but in this case, we write as ions when you write ionic reaction. Okay. Similarly, all the bases, potassium hydroxide, strontium hydroxide, barium hydroxide, these are strong bases. Okay. You learned in table 4.2. Okay. You will go there, and they are strong acid, strong bases. Strong acid, strong bases are all strong electrolytes, and so they dissociate completely, and therefore it is important. First step is to see if they're strong or weak, because if they are weak, then writing ionic reaction, you have to write the formula, okay, of the molecule instead of ions. We'll see later. Also pay attention to the solubility of the product. You need to determine maybe the reaction will forms a precipitate. Let's look at A, hydrochloric acid and potassium hydroxide. So here is the molecular equation: hydrochloric acid, potassium hydroxide, and because the acid-base reaction, proton hydroxide forms water and a salt. In this case is potassium chloride. Now, hydrochloric acid is a strong acid. Potassium hydroxide is a strong base, so the both dissociate completely into ions. So when we write ionic reaction, we should write hydrogen ion, chloride ion, potassium ion, hydroxide ion. And potassium hydroxide chloride is a strong electrolyte. Okay, this salt is a strong electrolyte, also dissociate completely. Remember, its cation is a group 1 metal, okay, and therefore the salt is a strong electrolyte, so it dissociates into potassium ion, chloride ion. Now water is a very weak electrolyte, so we cannot write hydrogen ion, hydroxide ion. We have to keep the formula of water, all right, when we write a total ionic reaction. So potassium doesn't change, so it's a spectator ion. Chloride doesn't change, it's a spectator ion. And so the net ionic equation should be hydrogen ion, hydroxide ion forms water, and the spectator ions are potassium ion, chloride ion. And you will notice that for all those strong acids, strong base reaction, if all substances are soluble, the net ionic equation is always this. It's the proton plus hydroxide forms water. B. Strontium hydroxide and the perchloric acid. Similar to the last question, we write strontium hydroxide, perchloric acid forms water, and the salt, in this case, is strontium perchlorate. And also we notice these are is a strong base, a strong acid, a strong electrolyte. So we write all the ions, okay, strontium ion, hydroxide ion, hydrogen ion, perchloric ion, strontium ion, perchlorate ion, and water keep as the formula because it's a weak electrolyte. So we see strontium is a spectator ion, and perchlorate is a spectator ion. So what left is 2 hydrogen ion, 2 hydroxide ion, 2 water. And so we divide by 2 and we get this final net ionic equation. Again, the same as last one, right? Because it's a strong acid, strong base reaction, and all substances are soluble. So its net ionic equation is just the hydrogen ion, hydroxide ion forms water, and the spectator ions are strontium ion and perchlorate ion. In C, barium hydroxide and sulfuric acid. So similarly, we write as barium hydroxide, sulfuric acid forms water, and the salt, in this case, is barium sulfate. Now here is the difference. This is a strong base, this is strong acid, so they all dissociate into ions. But barium sulfate is a not strong electrolyte, so it's insoluble. If you look at the solubility rule, most sulfate ion salts are soluble except the group 2 metals. So barium is one of them. So it's a precipitate. And therefore, when we write ionic equation, we have to keep this formula instead of writing ions. So here is the total ionic equation. So the reactants are all strong electrolytes. They ionize into ions, but the salt, the product, is the formula barium sulfate. That's a precipitate. And water is a weak electrolyte, so you keep it a formula. Okay, so you can see there's no substance in this equation that is unchanged before and after reaction, and therefore there's no spectator ion. And because no spectator ion, so the net ionic equation is the same as this total ionic equation. Okay, and there's no spectator ions. Now this reaction neutralizes acid base into water, so it's a neutralization reaction. It also forms a precipitate, so it is both a neutralization reaction and a precipitation reaction. In summary, for strong acid, strong base neutralization reaction, the net ionic equation is always hydrogen ion, hydroxide ion forms water. Unless the product salt is an insoluble salt, such as this one, barium sulfate, then the net ionic equation, you need to keep this salt, and the total ionic equation is the same as the net ionic equation. Let's take a closer look at a strong acid, strong base reaction. In strong acid solution, strong acid such as hydrochloric acid dissociate completely into hydrogen ion and chloride ion. The hydrogen ion immediately combine with a water molecule to form a hydronium ion, where oxygen bonds to 3 hydrogen atoms. When base is added, the hydroxide take a proton away from the hydronium ion, so hydroxide becomes a water molecule. The hydronium ion loses a proton and forms another water molecule. So you have seen that in the previous slides we showed for strong acid, strong base reaction, the net ionic reaction is a hydrogen ion and hydroxide ion combine to form water molecule. And this seems to be a simplified version of the strong acid, strong base reaction. In reality, it's the hydronium ion transfer a proton to hydroxide. So hydroxide becomes a water, hydronium ion also becomes water, so it becomes 2 water molecules. Now the chloride ion, the anion, and the metal, for example sodium, from sodium hydroxide, these are spectator ions, so they exist in a solution before reaction, and they exist as solution in the solution after reaction, so they are unchanged. However, if you heat the product, when the water molecules evaporate, the spectator ions combine by electrostatic force and becomes a crystalline solid salt, that, for example, sodium chloride salt. When sodium bicarbonate, which is a weak base, combine with acetic acid, which is a weak acid, water molecules is formed. At the same time, the solution forms a lot of bubbles, indicating a gas formation, and the gas is the CO2. Before we explain this reaction, let's start with sodium bicarbonate reacting with a stronger acid, hydrochloric acid. In solution, sodium bicarbonate is a strong electrolyte, so it dissociates into sodium ion and the bicarbonate anion. And hydrochloric acid dissociates into hydrogen ion, chloride ion. This weak base combined with hydrogen ion and give a conjugate base, which is a conjugate acid. Okay, this is a weak base, become conjugate acid, carbonic acid. Carbonic acid plus the spectator ion, sodium ion, chloride ion. Now, whenever you see this carbonic acid, you should know that this is a very unstable substance. It immediately decomposes into water and the CO2. Okay, so if you count the number of atoms, reactant has 2 hydrogen, product has 2 hydrogen, reactant has 1 carbon, product has 1 carbon, reactant has 3 oxygen, product has also 3 oxygen. So this is a reaction that you should immediately remember when you see this carbonic acid. Okay, therefore the net reaction between sodium bicarbonate and hydrochloric acid is this. You cancel this bicarbonic acid because this is a product but also a reactance, so they cancel each other. So the net reaction is sodium ion bicarbonate anion, hydrogen ion, chloride ion forms water, CO2, sodium ion, chloride ion. Okay, that's the total ionic reaction. Now, these are the spectator ions. So the net ionic equation is bicarbonate anion, hydrogen anion forms water and CO2. Okay, so it's a typical reaction when you have bicarbonate anion with acid. You forms water and the gas phase CO2. All right, now let's go back to the reaction of sodium bicarbonate with weak acid. Okay, now weak acid, acetic acid, does not dissociate as hydrochloric acid, forms hydrogen ion and the anion. Instead, it remains as a molecule. So when you write a total ionic reaction, it is the acetic acid molecule here as a reactance. But this one donate proton to react with this bicarbonate anion to form just like here, carbonic acid. Okay, and the carbonic acid immediately decomposes into water and the CO2. So that's why you see CO2 and water. This is because the acid has a proton that react with this bicarbonate anion to form carbonic acid, which immediately becomes CO2 and water. And the acid now becomes a conjugate base, which is acetate anion and the sodium ion. So sodium ion is a spectator ion. Okay, but this one is not. The acetate anion is not a spectator ion because this acid is not a strong acid. So in the reactants, it's the molecule. So it changed before and after reaction. And therefore, the net ionic reaction is the bicarbonate anion, acetic acid, CO2, water, and acetate anion. Sample problem 4.14. Write balanced total and the net ionic equations for the following reactions and use curved arrows to show how the proton transfer occurs. A. Hydriodic acid and the calcium hydroxide. Give the name and the formula of the salt present when the reaction water evaporates. B. Potassium hydroxide and the propionic acid. In A, first we notice that both hydriodic acid and the calcium hydroxide are strong acid and strong base. So they dissociate completely. For acid, it dissociates into hydrogen ion combined with water forms hydrogen ion. In base, it gives hydroxide ion. So let's write the ionic reaction. So hydriodic acid forms hydrogen ion and iodide. And the calcium hydroxide forms calcium ion and hydroxide. Okay, so you need to have two hydroxide to balance the charge of calcium. Now, when they react, we already know it is the hydrogen transfer from this hydrogen ion to hydroxide. Okay, now because we have two hydroxide, so you need two hydrogen ion. Okay, and if you have two hydrogen ion, the iodide must also have two. Okay, because you have hydrogen iodide, and so one hydrogen forms one hydrogen ion. You need two of them to form two hydrogen ion and two iodide. Okay, now when hydrogen ion transfer hydrogen to hydroxide, it forms water molecule. So two water molecule comes from two hydroxide. Now, two hydrogen ion, when they lose water, hydrogen ion, they also forms water molecule. So in total, you have 4 water molecules. 2 comes from hydrogen ion, 2 comes from hydroxide ion. Okay, and the spectator ions are calcium and 2 iodide. So that's the total ionic equation. Now, when we can eliminate the spectator ions, okay, so these are the spectator ions, then we have net ionic equation, which is hydrogen ion, hydroxide forms water. So again, it's the transfer of hydrogen from hydrogen ion to hydroxide to form 2 water molecules. That's the net ionic equation. So when the water is evaporated, if you look at here, okay, if water is evaporated, what left is just the spectator ion. Spectator ions are iodide and the calcium. Okay, so these 2 left attracted by electrostatic force and forms a solid. That's calcium iodide. In B, we notice that the acid, propionic acid, is a weak acid, and therefore it remains as a molecule, as a reactant, instead of dissociate into ions. So when we write total ionic reaction, potassium hydroxide dissociate into potassium ion hydroxide ion, but the propionic acid remains as a molecule. And then this acid, okay, combined with the base, so the proton with the hydroxide forms water, and acetate forms a conjugate base, acetate anion in the product. So water and acetate anion comes from the combination of these 2. Potassium doesn't change during the reaction, so it's a spectator ion. All right. So if we cancel the spectator ion, we got a net ionic equation, which is the acid with hydroxide forms water and acetate anion. And again, the spectator ion is potassium. Suppose we have an acid whose molarity is unknown, and we want to find the molarity. One way to do it is to use a base, such as sodium hydroxide, with a known molarity. Okay, let's say 0.3 molarity. And we add the sodium hydroxide into the unknown acid. And thus the reaction is a neutralization reaction. So hydrogen ion from the acid, hydroxide from the base added to the solution forms water. And we measure the volume added to it until the number of moles equal. Okay, so these 2 equal. And then because we know the volume, so we know the moles of hydroxide, and therefore we know the moles of hydrogen ion, and therefore we can calculate the molarity of the acid in the solution. And this process is called acid-base titration. In a titration, the concentration of one solution here is used to determine the concentration of another. In an acid-base titration, a standard solution of base is usually added to a sample of acid of unknown molarity. But how do we know these 2 number of moles equal? Okay, we add a indicator. So a acid-base indicator has different color in acid and base. So initially, you add an indicator to the acid. So it's an acidic solution. It has a color indicator. For example, the color may be red in acid. Now when you add a base, okay, the reaction occurs, the acid becomes smaller and smaller until it all becomes consumed and becomes base. So when you have excess amount of hydroxide, so now it becomes a base, and the color change, let's say, to blue. So the color, when the color change from red to blue, then you know the reaction reaches the end point. Okay, and so this indicator has different color in acid base and is used to monitor the reaction progress. And at the equivalence point is when this number of moles exactly same, the acid and the base exactly same. That's the equivalence point. The moles of hydrogen ion from the acid equal to moles of hydroxide produced by the base. Okay, now sometimes the indicator change color not exactly at the end point, not at the equivalence point, and the color change point is called end point. Okay, you want the end point as close as possible to the equivalence point so that you can measure the number of moles of the acid accurately. This diagram shows an example of acid-base titration. So this is an Erlenmeyer flask, contains an unknown acid with the indicator. In this case, the indicator may be phenolphthalein, which is colorless in acidic condition. So we add hydroxide, for example, sodium hydroxide in burette, okay, into this Erlenmeyer flask, and neutralization occur. So the acid in this solution is consumed gradually until it close to the end point. So at end point, so almost all acid is consumed. Now, if you add one drop of base into the solution, you start to see color change. But if you shake it, the color disappear again. So you add more, okay, more hydroxide until the one drop of base hydroxide will change color permanently. In this case, is a pink color. That means the end point is reached. And so you measure the volume of the base you added. Okay, if you know the molarity of the base, then you know the number of moles. So hydroxide, number of moles, how much moles base added to the solution. And because this number of moles equal to the moles of the hydrogen ion, so you know the number of moles of hydrogen ion, and if you know the volume, initial volume, then number of moles divided by volume, that's the molarity of the original acid solution. Sample problem 4.15. A 0.1 molarity of hydrochloric acid is used to simulate the acid concentration of the stomach. How many liters of stomach acid react with one tablet containing 0.1 grams of magnesium hydroxide? So this is a neutralization reaction between base, magnesium hydroxide, and acid, hydrochloric acid. So let's first write the neutralization reaction. So this is magnesium hydroxide. Magnesium is 2+, and you need 2 hydrochloric acid to form magnesium chloride and water. Okay, so that balance the neutralization reaction. The given is grams of this magnesium hydroxide. And the question is how many liters of hydrochloric acid, so the volume. We are asked the volume. Okay, so we know that we need the number of moles because stoichiometry based on moles of magnesium hydroxide and 2 moles hydrochloric acid. All right, so first 0.1 gram should convert to number of moles of magnesium hydroxide. And then based on stoichiometry, we can calculate moles of hydrogen chloride, hydrochloric acid. And then we can use molarity as a conversion factor to calculate the volumes of hydrochloric acid. Okay, so first calculate the moles. So we use grams of magnesium hydroxide divided by the molar mass. Okay, so 1 mole equals 58.33 grams. So gram cancel, give you moles of magnesium hydroxide. All right, now let's use stoichiometry. So 1 mole magnesium hydroxide, 2 moles hydrogen chloride. So moles magnesium hydroxide cancel, give you moles of hydrochloric acid. Okay, so next we use molarity as a conversion factor. So moles here, molarity you write as 0.1 mole is equivalent to 1 liter. We cancel moles, we get volume, liter. Okay, so the answer is 3.4 times 10 to the minus 2 liter of hydrochloric acid. Sample problem 4.16. A 50 milliliter sample of sulfuric acid is titrated with 0.1524 molarity sodium hydroxide. The burette reads 0.55 milliliter at the start and 33.87 milliliter at the end point. Find the molarity of sulfuric acid. So this is about titration using sodium hydroxide to titrate sulfuric acid. So here is the neutralization reaction, and it's a balanced equation. Okay, and it says the burette reads 0.55 milliliter at the start. So here is the Erlenmeyer flask with sulfuric acid, and the burette. Okay, here burette contains sodium hydroxide. All right, initially it's right here, which is 0.55 milliliter, and when you titrate, so some sodium hydroxide goes into Erlenmeyer flask, so volume decrease until it goes to here. The reading is 33.87. Okay, so the difference should tell you how much volume of sodium hydroxide is used to neutralize sulfuric acid. So the calculation give you volume equals 33.32. Use the final minus initial. So the end point volume minus at the start volume, and that's the how much volume of the base or sodium hydroxide goes into the neutralization. So now we know the given information is the sodium hydroxide molarity, which is this one. So we have molarity of sodium hydroxide, volume added sodium hydroxide. So both this given. We also know the volume of sulfuric acid, and we want to know the molarity. Okay, we want to calculate molarity. All right, so again, we first need to calculate the number of moles. So based on volume and the molarity, we can calculate the moles of sodium hydroxide. And then based on this equation, we calculate the moles of sulfuric acid. And with the number of moles and the volume, then we can calculate the molarity. Okay, so first calculate the moles of sodium hydroxide. So we have volume is added sodium hydroxide. Note that the volume is in milliliter. We change to liter. So it's 1 liter, 1000 milliliter. So milliliter cancel, give you liter. And then using the volume, we multiply by its molarity. Molarity is 0.1524 molarity, means moles sodium hydroxide per liter solution. So volume cancel, give you moles of sodium hydroxide. Okay, now let's calculate the moles of sulfuric acid. So based on this relation, so we have moles of sodium hydroxide. 2 moles sodium hydroxide is equivalent to 1 mole of sulfuric acid. So moles sodium hydroxide cancel, give you moles of sulfuric acid. Okay. Next, to calculate the molarity, we use moles divided by volume. So here is moles divided by volume. That's the molarity. Note the volume is milliliter. According to the definition of molarity, this should be liter. So we times a conversion factor, 1 liter, 1000 milliliter. So milliliter cancel. That gives you liter here. And that gives you molarity. And the answer is 0.05078 molarity. We have discussed the precipitation reactions, acid-base reactions. Next, we're going to talk about oxidation-reduction reactions or redox reactions. A redox reaction involves electron transfer. This is a diagram showing a redox reaction that forms an ionic compound. Magnesium metal reacts with oxygen gas, forms magnesium oxide. During the process, magnesium atom loses 2 electrons to form a magnesium cation 2+. At the same time, oxygen atom gain 2 electrons to form oxygen oxide, oxygen 2-. So we have 2 half reactions we can draw here. Magnesium atom lose 2 electrons to form magnesium 2+. At the same time, oxygen gain 2 electrons to form oxide, so 2-. Now this first half reaction is called oxidation reaction. Oxidation means it involves loss of electrons. So here magnesium lose 2 electrons. And so we can say magnesium is oxidized to magnesium 2+. Now this half reaction is called reduction reaction. Reduction reaction is the gain of electrons. Oxygen gain 2 electrons. So we can say oxygen is reduced. So reduced to oxide anion. These 2 half reactions occur together. If one is oxidized, there must be one reduced. One gain electron, there must be lose electron. And so in this sense, we can say oxygen is oxidizing reagent. So oxidizing agent to allow this oxidizing reaction to occur, because magnesium is oxidized. So oxygen is oxidizing agent. All right, without oxygen, this cannot happen alone. Okay, similarly, oxygen is reduced. So magnesium is called a reducing agent. So because of the magnesium, so reduction reaction can occur. So magnesium here is a reducing agent. In the last slide, we showed a redox reaction involves ionic compounds. Here we show a redox reaction involves covalent compound. So hydrogen is a non-polar molecule, covalent compound. Similarly, chlorine molecule also a covalent compound. All right. When these two combine together, it forms hydrogen chloride. And hydrogen chloride is a polar molecule because hydrogen and chlorine have different ability to attract electron. There's a electron shift from hydrogen to chlorine, and chlorine has more electron density and becomes partially negative charged, and the hydrogen atom is partially positive charged. So in this sense, chlorine gains more electron from hydrogen, and therefore we can say chlorine is reduced. Okay, so gaining electron, the reaction is reduction reaction. Similarly, hydrogen, because the electron shift to chlorine, so hydrogen is oxidized. Okay, and so when hydrogen is oxidized, chlorine is the oxidizing agent. And because chlorine is reduced, so hydrogen is a reducing agent. For redox reactions, in order to monitor which atom loses electron charge and which atom gain electron charge, chemists established oxidation number or oxidation state, which is the charge the atom would have if its electrons were transferred completely, not shared. For an atom in its elementary form, for example, sodium atom has an oxidation number 0. Oxygen molecule is in elementary form, so oxidation number is 0. For a monatomic ion, the oxidation number equals ion charge. For example, calcium, when lose 2 electrons, it is 2 plus, so it's cation 2 plus. The oxidation number is plus 2 with the sign before the numeral. So this is oxidation number, and this is the ion charge. Another example is aluminum 3 plus. So that's an ion charge, but the oxidation number is plus 3. The sum of oxidation number values for the atoms in a molecule or formula unit of a compound equals 0. This is because a molecule is neutral, so the sum of the oxidation numbers should be 0. On the other hand, for a polyatomic ion, the sum of the oxidation number values should equal to the ion's charge. For example, nitrate anion, nitrate has a negative charge, so the sum of the oxidation numbers of oxygen and nitrogen must be -1. Now here are the rules for specific atoms or periodic table groups. Group 1, because the charge is plus, so sodium plus, potassium plus, and therefore the oxidation number must be +1. For group 2, as I showed already, calcium 2 plus, beryllium 2 plus, so the oxidation number must be +2. So group 1 +1, group 2 +2. All right, and hydrogen is similar to sodium, potassium. It's also +1. Okay, in combination with non-metals. But if we combine with metals, then it's different. For example, in sodium hydride, so sodium hydride, sodium must be +1, and therefore in this case hydrogen will be -1, so they add together is 0. For group 7, fluorine, chlorine, bromine, iodine, oxidation numbers are usually -1. Okay, fluorine always -1, but for chlorine, fluorine, bromine, iodine, they are -1 in combination with metals, but and mostly non-metals. But there are exceptions. Okay, for example, if combined with oxygen, then it's not -1. All right. For oxygen, as we know, it's group 6, so the ion charge is -2. Okay, so 6 + 2 is 8, remember? So oxygen usually 2 negative. And so oxidation number is -2. So ion charge 2 minus, oxidation number -2. All right, there's an exception. That's hydrogen peroxide. In hydrogen peroxide, hydrogen is +1, oxygen is -1. Sample problem 4.17. Determine the oxidation number of each element in these species. Zinc chloride, sulfur trioxide, nitric acid, dichromate ion. These are the formulas for these compounds or ions. Zinc chloride, group 7, so ion, the oxidation number -1. Because we have 2 of them, so we add together should be -2. And the sum of the whole formula should be 0. And therefore, zinc must be +2. Okay. Next one, oxygen is -2. Okay. You have 3 of them, so the sum of the oxidation number of oxygen should be -6. In order for the sum of the oxidation numbers of the molecule is 0, sulfur must be +6. Okay, next, in nitric acid, hydrogen is +1 oxidation number, oxygen -2, And negative 2 times 3, so 3 oxygen, so negative 6. Okay, in order for the whole molecule to be 0, nitrogen must be plus 5. Okay, so 5 plus 1 equals 6. 6 minus 6 equals 0. So next one, dichromate ion. So oxygen is negative 2. You have 7 of them, so you times 7 equals negative 14. Now the whole ion has a 2 negative. All right, so the sum of the oxidation numbers must be negative 2. So the total number must be negative 2. In other words, the chromium ion added together should be plus 12. So negative 14 plus 12 will give you negative 2. All right. Now, in order for the chromium to be 12, each of them, you have 2 of them. So each of them must be plus 6. Okay. Sample problem 4.18. Use oxidation numbers to decide which of the following are redox reactions. For each redox reaction, identify the oxidizing agent and the reducing agent. So for these questions, we first need to assign oxidation numbers for each atom, and then note whether it changes as the reactants becomes product. If the oxidation number of atom changes during a reaction, we draw a tear line from the atom on the left side to the atom on the right side and label the change. For those reactions that are redox reactions, a reactant is the reducing agent if it contains atom that is oxidized. In other words, oxidation number increase. Okay, that's oxidized. And a reactant is oxidizing agent if it contains atom that is reduced or the oxidation number decreases. So let's look at question A. First, we need to assign oxidation numbers to all the atoms. Aluminum, hydrogen are in their elementary form, so the oxidation numbers are zeros. And in sulfuric acid, sulfate as a combined polyatomic ion, it should be negative 2. The charge, ionic charge, is negative 2. So the 2 hydrogen must be positive 2. Now because we have 2 hydrogen, so each one must be positive 1. Okay. Similarly, here sulfate is negative 2, but we have 3 of them, so the whole sulfate is negative 6 charge. And because we have 2 aluminum, 2 aluminum is positive 6, so each of them must be positive 3. Okay, so aluminum oxidation number is positive 3. Now, sulfate doesn't change, so for this question, we can keep it. We don't need to assign sulfur and oxygen because they combined as sulfate doesn't change. However, we can also determine the sulfur and oxygen charge. So sulfate, 2 negative. Oxygen is negative 2, so you have 4 of them, so should be negative 8 for 4 oxygen. And because the whole thing is negative 2 charge, and so sulfur must be positive 6. Okay, so sulfur positive 6 and oxygen negative 2. Okay, so let's assign here. All right, so here is the assigned oxidation numbers. So sulfate, as you can see, doesn't change. Okay, it doesn't change, but hydrogen and aluminum changes oxidation number, and therefore it is a redox reaction. Okay, now let's look at the aluminum. Aluminum change from oxidation number 0 to 3. Because oxidation number increase, it loses electron. It's oxidized. Aluminum is oxidized. This half reaction is oxidation reaction. Okay, so aluminum is oxidized, and therefore aluminum is a reducing agent. Now let's look at hydrogen. Hydrogen change from positive 1 to 0. So the oxidation number decrease. It must gain electron, and therefore it is reduced. The reaction is reduction reaction, and hydrogen is reduced. Okay, proton in this sulfuric acid is reduced. So sulfuric acid, this molecule, is oxidizing agent. I want to point out that if a reaction involves a polyatomic ion and the polyatomic ion in the reactant's product are the same, the numbers are the same. For example, in this case, 3-sulfate, product 3-sulfate. Then you can eliminate sulfate. Sulfate remains the same. It doesn't contribute to the redox reaction. Let's look at the question B. First, we assign oxidation numbers. Sulfate, again, oxidation number -2, and 2 hydrogen +2, each of them +1. And same thing is here, so -2, and sodium +1. So here hydroxide is -1, so sodium +1. And we can assign individually, oxygen is -2, hydrogen +1, and water, oxygen -2, hydrogen +1. Okay, as I explained in the last slide, we can eliminate the sulfate because the sulfate doesn't change. But we can also assign individually sulfur +6, oxygen -2, as we shown in the last slide. Same thing is here. Okay, so that's the oxidation numbers. So let me eliminate. Okay, so here is the oxidation numbers, and you can see none of atoms oxidation number change. So all of them remains the same. Therefore, this is not a redox reaction. So here is question C. First, we assign oxidation numbers. Oxygens are -2, -2, -2. And for the formula to be 0, lab must be +2. Same thing is carbon, +2. And this lab is elementary form, so it's 0. In carbon dioxide, there are 2 oxygen, so that it will be -4, and therefore carbon is +4. Okay, you can see lead change oxidation number. Carbon also change oxidation number. So these are the oxidation numbers, and therefore the reaction must be redox reaction. Okay, because there are elements change oxidation numbers. Now let's look at the carbon. The carbon change oxidation number from 2 to 4. It increase oxidation number, and therefore it must lose electron, and therefore it's a oxidation reaction. Carbon is oxidized, and therefore carbon monoxide is the reducing agent. Okay, and similarly, lead oxidation number decrease from +2 to 0, so it must gain electron. So lead is reduced. Okay, and the lead oxide, the compound, is the oxidizing agent. Okay. Here shows the summary of terminology for redox reactions. When a substance loses electron, it is oxidized. So cation lose electron, becomes cation 2+. So cation is oxidized. On the other hand, oxygen gain electron to form oxide, so oxygen is reduced. And when oxygen is reduced, it is called oxidizing agent. Okay, this is because oxygen gain electrons so that cation can lose electron and the cation can be oxidized. All right, and similarly, cation is called a reducing agent because cation loses electron so that oxygen can gain electron and becomes oxidized or becomes reduced. Okay, now when cation is oxidized to cation 2+, the oxidation number increase and from 0 becomes 2 plus 2. Okay, when oxygen is reduced, the oxidation number decreases from 0 to -2. In acid-base titration, we use a known concentration of a base to titrate an unknown concentration of an acid. In redox titration, we can use a known concentration of oxidizing agent to titrate an unknown concentration of a reducing agent. Here is an example of redox reaction. So permanganate, the oxidation number decrease, so it's an oxidizing agent. And the oscillate anion, the oxidation number increase to carbon dioxide, so it's a reducing agent. Okay, now suppose we have a solution of sodium oscillate, and we want to find the molarity. Okay, we can use potassium permanganate to titrate this unknown solution of sodium acetate. So we measure a certain volume of sodium oscillate, okay, solution, and we add the potassium permanganate into the burette and titrate the solution of sodium oscillate. Note the color of potassium permanganate is deep purple. Okay, but when we add the solution potassium permanganate into sodium oscillate, initially the color changes to colorless. Okay, this is because due to this redox reaction, whenever you add the potassium permanganate, it is reduced to manganese ion, which is colorless. Okay, until the reaction reaches end point. So at the end point, all sodium oscillate is oxidized, and so in the solution there's no sodium oscillate anymore. So one drop of potassium permanganate will change the color permanently into purple, and that indicates the end point. So at this point, if we measure the volume of potassium permanganate, and also we know the molarity, then we can calculate the number of moles of potassium permanganate, and from this we can calculate the number of moles of sodium oscillate according to this equation, okay, stoichiometry. So tells you 2 moles potassium permanganate is equivalent to 5 moles of sodium oscillate. So that gives you the number of moles. With the volume, we can calculate the molarity. Sample problem 4.19. In this problem, we want to measure calcium cation concentration in 1 milliliter of human blood. And to do that, we use sodium oscillate solution to precipitate calcium ion into calcium oscillate as a solid. Now, if we know the amount of calcium oscillate solid, then we know the amount of calcium ion in the solution. To find the amount of calcium oscillate, we dissolve it in dilute sulfuric acid so that it becomes dissociated oscillate anion. Okay, the advantage to do that is this can be measured by titration using this redox reaction, as we shown in the last slide. So potassium permanganate is the oxidizing agent, which will oxidize the sodium oscillate. All right. So it was found that we need 2.505 milliliter of 4.88 times 10 to the minus 4 molarity potassium permanganate to reach the end point. So for the titration, we measure the volume, which is this one, 2.05, and we know the molarity, so this molarity for potassium permanganate. Okay, so as usual, this needs to be converted to number of moles of potassium permanganate. And from moles of potassium permanganate, and using the stoichiometry here, okay, the equation, we can find the moles of calcium oxalate. All right, and then from the equation, okay, we can convert moles of calcium oxalate to calcium, number of moles of calcium. Okay, so that's what is asked for, to calculate the amount, number of moles of calcium ion in the blood. So we first find the moles of potassium permanganate, and then we use stoichiometry to find moles of calcium oxalate, and then to find the moles of calcium ion. First, we calculate the moles of potassium permanganate, and we start with the volume, which is 2.05 milliliter. We convert to liter using 1 liter 1000 milliliter. So milliliter cancel, give you liter, the volume. And then we multiply by the molarity. Molarity is 4.88 times 10 to the minus 4 molarity, means moles per liter. So volume cancel, give you moles of potassium permanganate. Okay, now using the moles per potassium permanganate, we want to calculate the moles of calcium oxalate using stoichiometry. So here is the moles potassium permanganate, and then the conversion factor. 2 moles potassium permanganate is equivalent to 5 moles calcium oxalate. So moles potassium permanganate cancel, give you moles of calcium oxalate. Okay, the next step, we want to find the moles of calcium. So in this equation, the ratio is 1-to-1 ratio. So this is moles of calcium oxalate, and the ratio is 1-to-1. 1 mole calcium oxalate give you 1 mole of calcium. So that is the moles of calcium ion in the solution. Redox reactions can be further classified as the following types of reactions. Combination reactions, where 2 or more reactants combine to form a new compound. For example, iron rust. Iron reacts with oxygen, forms iron oxide. Okay, it's 2 elements combine to form a compound. Decomposition reactions, where a single compound decomposes to form 2 or more products. An example is calcium carbonate. When heated, decompose into calcium oxide and carbon dioxide gas. In displacement reactions, the number of substances on the 2 sides remains the same, but atoms or ions exchange places. Okay, one displacement reaction is called a single displacement reaction. So an example is a compound YZ, the Y is replaced by element X. So YZ becomes XZ. All right, so that's a single displacement reaction. In double displacement reaction, for example, B and D exchange position, so the compound AB becomes AD and CD becomes CB. Combustion reaction is the process of combining oxygen and usually release heat. An example is carbon monoxide react with oxygen, forms carbon dioxide. Here shows a redox reaction. Potassium reacts with chlorine, forms potassium chloride. What type of redox reaction is it? Yes, it's a combination reaction, where 2 reactants combine to form a new compound. Potassium is a reactive metal usually kept in a liquid oil to prevent exposure to moisture and oxygen. Chlorine is a reactive gas which has a color of yellow-green. Now when this potassium metal is placed into the gas chlorine, the 2 elements react violently. You can see it emit light and heat. The product is a white solid. That's the potassium chloride salt. In this redox reaction, mercury oxide, when heated, it forms mercury and oxygen. So what type of redox reaction is it? Yes, it's a decomposition reaction, where a single reactant decomposes to form two products. Mercury oxide is an ionic compound that has a color of red orange color. Okay, when heated here, the compound gains enough energy, and the oxygen anion lose electron to form oxygen gas, and the mercury ion gain electron to form mercury. And you can see in this test tube the shiny liquid mercury on the bottom and the oxygen gas on the top of it. In this redox reaction, lithium reacts with water, forms lithium hydroxide and hydrogen gas. What type of redox reaction is it? Yes, it's a single displacement reaction. One of the hydrogens of a water molecule is displaced by a lithium atom to form lithium hydroxide, and the hydrogen forms hydrogen gas. When lithium metal is placed inside water, a lot of bubbles forming, and this indicates the formation of a gas phase. Lithium loses electron to form a lithium cation, which is solvated by water molecules inside the solution. At the same time, a water molecule gains an electron. When the water gains electron, bond break. Okay, one side forms hydroxide, and the other side forms a hydrogen atom. When two hydrogen atoms combine, it forms a hydrogen gas. In the last slide, we showed a redox reaction where lithium metal can displace a hydrogen from water molecule to form hydrogen gas. There are other metals can do the same reaction, such as sodium, potassium, calcium, and these are the most reactive metals. Now there are other metals that they can do similar reaction but must under heat. For example, aluminum can displace a hydrogen from water from hydrogen gas, but must provide heat. And this is because water molecules, okay, there's bonds. To displace a hydrogen, these bonds must break, so you need energy. Okay, these metals are slightly less reactive metals than potassium, sodium, lithium, the most reactive metals. So the displacement reaction must be done under heat. Okay, another example is zinc. Now there are still less reactive metals that even under heat, they cannot displace hydrogen from water molecule to form hydrogen gas. On the other hand, if you provide proton instead of hydrogen from water, okay, for example, hydrogen chloride dissociate into proton and chlorine. So this bond can easily break in water solution. Then this still less reactive metal can displace hydrogen from hydrogen chloride acid. So one example is nickel. So nickel can displace a proton from hydrochloric acid or sulfuric acid. So any acid, the proton can be displaced by nickel to form hydrogen gas. Okay, another example is tin. So these are still less reactive metals. They can displace hydrogen from an acid to form hydrogen gas. Now here diagram shows nickel metal, all right, in acid solution such as hydrochloric acid, and you can see bubbles coming out, and that's the gas hydrogen. The least reactive metals cannot displace hydrogen from any of these hydrogen sources, either water or neither water nor acid, even strong acid. Okay, these metals do not react with even strong acid, and these are precious metals such as silver, gold, platinum, and that's one reason they can be used for jewelries, because they don't react, they are stable. I want to clarify that for the reactions involving slightly less reactive metals, heat is provided as steam. So aluminum, zinc can only displace hydrogens from steam instead of water itself. In all these displacement reactions, the metals, the oxidation number change from 0 to positive, positive 1, positive 3, positive 2. So these metals are oxidized. So the reactions are oxidation reaction. Okay, and the hydrogen, so in water is positive 1 becomes 0. So positive 1 becomes 0. So the hydrogen ion is reduced. Okay, this is a reduction reaction. Okay, and therefore these metals is also called a reducing agent. And therefore you can see these metals, they have different reducing power. Because lithium can reduce hydrogen in water, so it's the strongest. These metals, lithium, sodium, potassium, are strongest reducing agent. So strongest reducing agent. And aluminum, zinc, they are less stronger, so they are weaker because they can only reduce steam, hydrogen in steam, okay, hydrogen ion in steam. And nickel, okay, tin, they are even weaker reducing agent. They can only reduce proton in acid. And precious metals, okay, these are the weakest reducing agent. Okay, they cannot reduce proton in acid. The reducing power of the metals is summarized in this chart. On the top of the chart are the strongest reducing agent. So strong. And on the bottom is the weakest reducing agent. Okay, so lithium, potassium, barium, calcium, sodium, and these are strong reducing agents, and they can reduce hydrogen ion from water. Okay, or you can say they can displace hydrogen gas from water. Okay, metals, magnesium, aluminum, manganese, zinc, chromium, iron, cadmium, they can reduce hydrogen ion from steam. Okay, you need the heat, so from steam, or they can displace hydrogen gas from steam. Okay, metals including cobalt, nickel, tin, lead, they are weaker reducing agents. They can only displace hydrogen gas from acids, or you can say they can reduce protons in acids. Okay, here is the hydrogen gas itself. So any metals above it can replace or displace hydrogen gas from either water or steam or acids. Okay, metals below it cannot displace hydrogen gas from any source. Okay, these include copper, mercury, silver, gold. Okay, so this table not only tells us the reducing power of the metals comparing with hydrogen gas. We can also use this table to compare two metals. Okay, for example, let's compare aluminum with, or let's say magnesium. Let's say magnesium and zinc. Okay, let's compare magnesium. Now, because magnesium is above zinc, so magnesium has a stronger reducing power than zinc, and the magnesium can displace zinc from its cation or ion solution. For example, if you place magnesium bar inside a solution containing zinc cation, then magnesium can dissolve, becomes magnesium ion, and the zinc ion becomes zinc metal. In other words, magnesium displaces zinc from the zinc ion solution. Okay, because magnesium is a stronger reducing agent than zinc. Okay, it can reduce zinc cation to form zinc ion, zinc metal. All right. On the other hand, if you place, let's say, iron bar inside magnesium, well, nothing will happen because iron is here, magnesium is here. So iron is a weaker reducing agent, so it cannot reduce. Magnesium cannot reduce. Iron cannot reduce magnesium cation, so nothing will happen. Okay. Now, another example is copper and silver. So, although these two metals are weaker reducing agent than hydrogen, it cannot displace hydrogen. They cannot displace hydrogen, but because copper metal is a stronger reducing agent than silver, so it can reduce silver from its cation solution, so it becomes silver metal, and copper becomes copper 2+. So copper can reduce silver, all right, becomes silver metal. Okay, and on the opposite side, if you have silver placed in copper solution, nothing will happen. Silver cannot reduce copper ion because copper is above silver, has a stronger reducing power. Since copper is above silver, so copper has a stronger reducing power than silver. When a copper wire is placed inside the silver nitrate solution, silver nitrate solution contains silver ion. Okay, so copper will reduce the silver ion, silver cation to become silver metal, and you can see copper wire coated with silver. Okay, this is at the microscopic level, the silver atoms. Okay, and here the white shining solids, and at the same time, copper itself, the metal, becomes oxidized, becomes copper 2+, and the copper 2+ inside the solution is responsible for the blue color. Sample problem 4.20. Classify each of following redox reactions as a combination, decomposition, or displacement reaction. Write a balanced molecular equation for each, as well as total or net ionic equation for part C, and identify the oxidizing and reducing agents. To answer this question, we need to remember combination reactions combine reactants. Decomposition reactions involve more products than reactants, and the displacement reactions have the same number of reactants and products, but the atoms or ions exchange positions. Question A. Magnesium plus nitrogen forms magnesium nitride. This is the balanced reaction equation. Two elements combine forms a compound, so the reaction is a combination reaction. Now, because magnesium and nitrogen are both elementary form, oxidation numbers are 0. In magnesium nitride, nitrogen is -3, magnesium is +2. Okay, for nitrogen, oxidation number decrease, it gain electron, so nitrogen is reduced. The reaction is a reduction. Okay, because nitrogen is reduced, so magnesium is reducing agent. Okay, magnesium is the reducing agent. It reduces nitrogen gas to nitrite. Similarly, magnesium is oxidized, so oxidation number increase. Magnesium is oxidized, nitrogen is oxidizing agent. Next question. Hydrogen peroxide forms water and oxygen gas. So this is the balanced redox reaction. One reactant forms two products, even though you have a two coefficient, but both are hydrogen peroxide, and therefore the reaction is decomposition reaction. Okay, one type of reactants forms two different products. Okay, now because we only have one type of reactants, so hydrogen peroxide is both the reducing and oxidizing agent. In fact, if you look at oxygen inside the molecule, so one oxygen has a oxidation number -1, it goes to 0. So oxidation number decrease. That means it lose or increase. -1 goes to 0, increase. So lose electron, and therefore it's oxidation. So this is oxidation. Okay, and then there's another oxygen, also -1, but it forms -2. So it goes to here. So in water molecule, oxygen is -2. So the oxygen goes to -2, decrease oxidation number in gaining electron, and therefore it's a reduction reaction. Okay, so within hydrogen peroxide, two oxygen atoms, one is oxidized, one is reduced. All right, so the molecule is both oxidizing and a reducing agent. In question C, aluminum react with lead nitrate to form aluminum nitrate and lead. So here is the balanced redox reaction: aluminum, lead nitrate, aluminum nitrate, and lead. So aluminum displaces lead to form aluminum nitrate plus lead. So the reaction must be displacement reaction. Okay. Lead change oxidation number from 2 to 0. So it decreases oxidation number, and therefore it's reduced. Okay. Lead is reduced. Aluminum is reducing agent. So aluminum is reducing agent, and the lead nitrate is oxidizing agent. To write ionic reaction, we notice that salt containing nitrate must be highly soluble. So they must dissociate into ions. So we write aluminum, lead ion, nitrate ion, aluminum ion, nitrate ion, and lead. So in this equation, nitrate doesn't change before and after the reaction, so it's a spectator ion. So what left is the total ionic equation. That's aluminum plus lead, aluminum ion plus lead. So lead ion becomes lead, aluminum becomes aluminum ion. In principle, every reaction is reversible and will reach dynamic equilibrium if all the reactants and products are present. Let's take this decomposition reaction as an example. If we start with calcium carbonate, it will decompose into calcium oxide and carbon dioxide. But if we start with calcium oxide and carbon dioxide, they will combine and go back to calcium carbonate. So if we place calcium carbonate inside a closed container, so this container is closed, and heat it, calcium carbonate will decompose to become calcium oxide and carbon dioxide. Initially, we only have calcium carbonate, so the forward reaction proceeds. With time, more and more product form, and so the reverse reaction becomes increasingly important. At a certain point, the forward reaction, reverse reaction has equal reaction rate. At this point, the reaction reaches equilibrium, or called dynamic equilibrium. Okay, because the forward reaction and the reverse reaction still proceed, but they have the same reaction rate. So the amount of reactants and the product remains constant. They do not change, and that's the equilibrium. Now, if we place calcium carbonate in an open container, so this container is open, okay, and when we heat the reactants, it will decompose into calcium oxide and carbon dioxide, but carbon dioxide is a gas, so it can escape from the container. And because reactants a product escape from the container, so they cannot combine to go back to the reactants. So with time, more and more calcium carbonate is consumed until all calcium carbonate will be consumed, and the reaction will complete. And this is an example of a non-equilibrium system. There are other types of reversible reactions. One example is weak acid, weak base dissociation in water. We all know that strong acid, such as hydrochloric acid, in water completely dissociate into hydrogen ion and chloride ion. However, for a weak acid, such as acetic acid, okay, so this is a weak acid. In water, it dissociates into hydrogen ion and acetate anion. Okay, now these two also recombine and go back to the weak acid. And in water, there's only 1.3% of this acid dissociate, and then it reaches equilibrium. Similarly, we know strong base, sodium hydroxide, completely dissociate into sodium ion hydroxide ion. But for weak base, such as ammonia, all right, in water, it goes to ammonium and hydroxide. But then these two recombine, and go back to the weak base and reach equilibrium.